Well, as we enter section 2.0D, no, we're not in your book yet. We're still building a platform of matrices to make sure we've got it all down before we do so. And we'll now take a look at the issue of singularity and rank. And that will be the second to last section before we're all prepared to start using our numerical methods. So let's go ahead and attack that. We'll bring back our generalized matrix, and we'll call it A, just like we did before, and we'll also look at some vector B. Now notice this is a rectangular matrix. The number of rows is not necessarily the same as the number of columns. We're calling the number of rows M and the number of columns N. In this particular example, B also has N entries into it. That's actually on purpose, because if it didn't, our matrix vector multiplication is going to have some serious problems. So let's take a look at how we might define matrix A times vector B. So our approach will be to take a specific row of A and take its entries and in a pairwise fashion multiply them by the entries of vector B. We'll do it in this manner. We'll take A11 times B1, and we'll add that to A12 times B2. And we will continue to add these paired products until we get to the last one, A1n times Bn. The sum of all those paired products is going to be the first entry of a new matrix that I'm forming, which I'm going to call C. Now, it really was important that the number of entries of B was equal to the number of columns of A. If it had not been, then I would have either run out of A entries before I was done with the B's, or vice versa, and this process would break down. So it is required that the number of columns of A match the number of entries of B. So we'll take a look at this more formally. We're saying vector C is equal to matrix A times vector B only if A has the same number of columns that B has entries. When we create this vector C, it's going to have a dimension that will not be the same as the number of entries of B. Rather, it will be equal to the number of rows of A. Well, that makes sense, because we're going to repeat this process for every single row of A. So this same paired product that I did on the first row of A with the columns of B, I will do again with the second row of A and the same entries of B. And I do it a third time with the third row of A and the same entries of B, and each time calling the result C1, C2, C3, and so forth until I'm done. Well, when am I going to be done? I'll be done when I get to the last row of A, so I'm calling that C sub M. If you'd like a more mathematical way of writing that down, we use the summation sign, create this floating index of k from 1 to n, and it will correspond to the column position of A and the entries of B. And so this forms the same set of products, and this provides the summation, and the I is keeping track of the row number that we were computing on. So there's the method. Let's suppose we generalize B to be a matrix rather than a vector. Well, we can do that using the exact same approach. We might even imagine that the old vector B was loaded up in the first column of this new matrix B. Well, that would work exactly the same way until we ran out of values of vector B and started looking over at the second column. What do we do with that? Well, we do exactly the same thing, but we form a new vector C and repeat the whole process, and now we have two vector C's instead of one. And we could continue to do that for all these columns of B, ending up with n C vectors. Well, rather than doing that, why don't we just double index the C value, call it Cij, where I represents the row number and J represents now a column position, because what we're really doing is forming a new matrix C rather than just a series of column vectors. Now, if you do that, beware. You might be tempted to think you can do this in either order. You can take A times B, or equally take B times A, and that will almost never work. It's just A times B is not equal to B times A. except under some rare circumstances. Yes, you can come up with certain criteria, sometimes very useful criteria, that will result in A and B being commutative. In other words, you can change the order of multiplication. But in general, you cannot reorder multiplication of matrices. So what we're saying is matrix multiplication is not commutative. Let's look at some examples, because now we're going to introduce some trouble and see when we don't have enough data to actually solve a system. Now you've seen this before. This was our little electronics or mock electronics example. And out of that, we were forming a series of equations. And so let's go back and look at the constraints that the finance and the purchasing departments made. And let's suppose that the marketing group didn't make any constraints at this time. Now, I know last time we brought this example, there were marketing constraints, but let's just pretend that that didn't happen. Well, that's going to end up resulting in an insufficient number of equations to determine our solution. We're going to end up with 7 unknowns with only 6 equations. So here's where our budgeting limits, our purchasing requirements, our design requirements, I can only cook up 6 equations out of that, and that will necessarily result in insufficient information to come up with a unique solution. In fact, I might get an infinite number of solutions out of it, but I'm not going to get a unique solution. So we will call this situation singular. Okay, we'll also call it less than full rank for reasons that we will discuss very soon. Let's now make this situation a little less obvious. It's pretty obvious that if you end up with 7 variables and 6 equations, you can't solve it. I think we all would have expected that. But what if you do have the right number of equations and it matches the number of unknowns? Does that guarantee that you will get a unique solution? So let's go back again and say, well, let's suppose the finance department dropped their budget limit per lot. And so there's no purchasing constraints, but the marketing department still has some constraints that we're going to throw in there and see what that ends up with. So again, we're asking how many products X, Y, and Z we're trying to make. So if we add those all up, these were those 3 marketing constraints. Here were our design constraints. Looks like there's 7 equations there to me. And if I just sort of rephrase this more complicated conditions and put it in what we'll nicely put into a matrix system, then I should be able to take these 3 equations, these 4 equations, maybe we want to move R, C, and T, and B to the left-hand side after we negate them to be able to put constants on the right and variables on the left. But after we do that, we end up with a little more organized set of equations, all nicely lined up in columns. Well, that becomes an invitation of putting it into a matrix and vector notation, which would look like this. So now I'm feeling better. It's kind of a big system. I don't think I'd want to solve this in my linear algebra class without some numerical methods, but at least it looks solvable because I have 7 equations and 7 unknowns. Well, turns out it's not. This is still what we call a singular system. It's not obvious that it's a singular system, and so we are going to have a need in our numerical methods to find out when something is or isn't singular, or we could really chase the computer off into some problems that go out of control. So we're going to have to think that through very carefully. So this is going to be what we call a non-singular system. Now that's too big for me to deal in this slide, so I'm going to simplify it and see if I can create another singular system that's smaller. And this one is also going to do the same thing. So this is a portion of what we had before, and my method of choice is to try to reduce this system into echelon form. Okay, we know how to do that. We stick it in our augmented form. We come up with appropriate row transformations in order to get rid of these values because we'd like zeros under here. We already have our coveted 1 in this upper left-hand corner, so that sounds great. And we continue to try to get it into echelon form, and look what happened. We got there, but we ended up with a 0 in this location. And that is going to be a problem because that also with it brings an entire row of zeros. the rank of a system is going to be equal to the number of non-zero rows. So this is going to have rank 2. We will also call this less than full rank because the rank is less than the number of rows. And I can't solve this one. Well, I could solve it in terms of vector spaces and so forth, but I'm not going to go there right now. I'm looking for a unique solution, and I'm not going to get that unique solution. So we are implying through this echelon reduction that the system is singular. Okay, so let's formalize this term rank. I just used it. I kind of told you what it was already, but let's formalize it. And the way we're going to find out the rank is you're going to reduce A through this Gaussian reduction so that you get it to echelon form. And if you may, well, you may end up getting some zeros in a diagonal. If it happens, it happens, but you get it down to that point. You're either going to have ones or zeros in the main diagonal, and what you'll do is take the trace, and that trace is going to be now called the rank of A. You think about that, that is the number of non-zero rows. If it turns out that your rank equals the row dimension, then we say it's full rank and you can go ahead and solve it and get a unique solution. If not, then it's going to be called singular. If it's full rank, we call it non-singular. You could also call it invertible. Now we'll save that to the next section. If it is singular, then you're not going to be able to get a unique solution, and you're going to have to write that into your software as a check to make sure that you don't try to do something that can't be done. So that ends this particular section, 2.0D, and we have one more preliminary section that will get us completely ready for our numerical methods in 2.1, and that will be to study inverses, and we'll do that next time.